Okay, so now that we've discussed the quantum model of an atom, let's talk about electron configuration. Electron configuration shows up pretty frequently in the MCAT, and they're usually in fairly straightforward questions like, what is the electron configuration of this atom? And in order to answer those questions, you need to know the rules for writing out the electron configuration, as well as a few notable exceptions. So to begin, let's talk about what exactly is the electron configuration. So if you recall in our last video, we said that the electrons can reside in all of these different orbitals within these different shells and subshells. When we're looking at electron configuration, it's essentially a notation that we can use to illustrate where all the electrons are in an atom, in which shells and subshells and orbitals do we have electrons. And this is generally for atoms in their ground state. So that means they're at the lowest energy state possible. And the way we want to talk about how we add electrons to the different orbitals, it's good for us to do a quick review of the Bohr model and the quantum model. So if you recall in the Bohr model, we have electrons that reside in these different energy levels. So here I've drawn a few examples of energy levels. So the n equals 1 energy level is, of course, the lowest in energy and closest to the nucleus. The second energy level is higher in energy and farther away from the nucleus, and the same as you go from the third to the fourth. You'll also notice what we've described before, which is the energy gap between the first and the second shell is the largest. It's larger than the gap between 2 to 3, which is larger than that between 3 and 4. Now, here in the Bohr model, all of the electrons in the shell have the same energy. You'll recall that's not the case in the quantum model. In the quantum model, each energy level or shell can be divided into subshells, and each subshell is going to have different energies. And you can tell this based off the complexity of the shapes of the orbitals in the subshell. So you recall that we have 4 different types of subshells. We have the S, P, D, and F subshells. And as you go from S to P to D to F, your subshells become increasingly more complex. And at the same time, your subshells also increase in energy. So that means S is the lowest in energy, and F is going to be the highest in energy within an energy level. So let's look at how this manifests within the quantum model within this energy diagram. So it's similar in that we have the first energy level, which is the lowest in energy and closest to the nucleus. Here we have one subshell. That is the 1s subshell, and that's it for our first energy level. In our second shell, we're going to have the 2s subshell as well as the 2p subshell. You can note, first of all, that our s subshell only contains 1 orbital, but our p subshell contains 3 orbitals. You can also see here that because the p subshells, you have the orbitals that are dumbbell shaped that are more complex than the spherically shaped orbitals in the s subshell, that electrons in the 2p subshell are slightly higher in energy than the electrons in the 2s orbital. You can then move on to the 3s subshell, or the third shell, where you have the 3s subshell, you have the 3p subshell, and you also have the 3d subshell. So 3d subshell, being a d subshell, of course has 5 orbitals, and as you increase in complexity from s to p to d, you have higher and higher energy. And as it turns out, this increase in energy combined with the fact that the energy levels get progressively closer together as you move away from the nucleus actually results in the 4s subshell being lower in energy than the 3d subshell. But by the time you get to the 4p subshell is higher in energy. So that means as we're going from lowest to highest energy, we'd go from 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, and so forth. Now, this is important because when we're drawing the electron configuration of an atom in its ground state, we fill orbitals from lowest to highest energy. So this order that I drew out is the exact same order that we would follow for writing out the electron configuration. So for instance, let's take a look at an example with aluminum. So when you're taking a look at aluminum, you can see in the periodic table that it has an atomic number of 13. That means that neutral aluminum atoms have 13 protons and also 13 electrons. So we would want to take the 13 electrons and fill them from lowest energy orbital up. So if we go ahead and do that, we can get the following electron configuration, where we'll have 1s2, 2s2, 2p6, 3s2, and 3p1. Now there's a few different parts of this notation you'll want to be aware of. The number in the front, the 1, the 2s, and the 3s, that corresponds to the shell number, right? Basically the first shell, then the second shell, then the third shell, and so forth. The letter in the middle corresponds to the subshell. So that means here I'm filling electrons in the 1s subshell, then the 2s subshell, then the 2p subshell. The exponent on the top, the superscript, that represents the number of electrons within that subshell. So if I have a 2 for s, that means I filled up that s subshell because the s subshell can hold 2 electrons. If I have a 6 by the p subshell, then similarly I filled that p subshell with 6 electrons. But here, since this is 3p1, that means I only have 1 electron in that p subshell, so I could, in theory, put in 5 more electrons in that subshell. Now, this notation, while we can follow this diagram that I just drew right here, there's actually a much simpler approach on the MCAT, and that is, if you take a look at the periodic table, this is simply following the periodic table, starting from hydrogen on the top left, and working left to right, top to bottom. So generally, all you have to do is follow the periodic table to figure out the electron configuration. So you'll make note here that this follows the periodic table from left to right and top to bottom. All right. One other thing that we're going to see shortly is that this is sort of the long way of writing out the electron configuration. If you want to draw everything out, there's a way that we can come up with a shorthand notation using noble gases. We can take a look at that with an example here with iron. So iron, if you take a look at the periodic table, you're going to find that it's a transition metal within the 4th row of the periodic table. And if we were to draw out the long form of the electron configuration, then we can do the same thing. We can say we've got 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Remember, when you get to the d block, you have to subtract 1 for the principal quantum number. So here it's going to be 4s2, 3d6, because iron is the 6th element in that d block. Now, you can start to see that this is becoming pretty tiresome, right? This is a lot to have to write out. So that's why we often have a shortcut where we use what is called noble gas notation. So with noble gas notation, you will draw out the same electron configuration, but instead of starting with 1s every single time, you're going to look at the last noble gas before that element. So if we take a look at the periodic table, the last noble gas before iron is argon. And what you would just do then for iron is you would put argon in brackets. When you write argon in brackets, that means you're representing all the electrons starting from hydrogen all the way through argon. So you just have to write what's left after argon, which would just be 4s2, 3d6. So both of these notations are acceptable for the MCAT, and it'll just depend on what you see in the answer choices. All right. Now, this is describing for us how we fill electrons from lowest energy to highest energy. It's actually important to note that the order we fill the orbitals is not the same order that we remove electrons from the orbitals. When we remove electrons from the valence shell orbitals. So first of all, valence shell is the outermost shell with electrons. So you're removing electrons from the valence shells from the highest energy orbitals to the lowest energy orbitals. And this is pretty important because, for instance, if I take a look at iron, its outer electrons, which you would think of as after argon, you have 4s2 and 3d6, at least based upon our electron configurations. Usually you would think, okay, when I filled electrons, I filled 4s then 3d. So if I remove, I should remove in the reverse direction. I should remove 3d then 4s. But that's not the case. So you have to be careful here. So if you see here, you have electrons in the 4s subshell and electrons in the 3d subshell. Between these two shells, the fourth shell and the third shell, the valence shell is the fourth shell. Right? This is the third shell. That's not the outermost shell. The outermost shell is the fourth shell. So that means when you remove electrons, you have to remove electrons from the 4s subshell before you can remove electrons from the 3d subshell. That would mean, for instance, if we were to look at the electron configuration of iron 2+, where we've lost 2 electrons, that electron configuration would be argon 3d6, where you've taken away 2 electrons from that 4s subshell. And we can actually summarize this, that in general, when you're looking at rows such as the 4th row of the periodic table, the order that you fill is just based on the periodic table. So you first have the 4s, and then you have the 3d, and then you have the 4p. So that's the order you would fill the electrons in the orbitals. However, when we're removing electrons, we have to remove electrons from the valence shell. So the valence shell, we've got the third shell and the fourth shell here, so you would remove from the fourth shell. Now you do remove from highest energy to lowest energy, so you would remove the 4p first. So here we remove 4p, then we remove 4s, and then we remove 3d. So that illustrates the difference between how we fill electrons in orbitals versus removing electrons from orbitals. All right. Another important rule for electron configurations is Hunds Rule. Hunds Rule describes how we fill electrons within degenerate orbitals. So the first thing we want to know is what exactly are degenerate orbitals? And as we can see here, degenerate orbitals are simply orbitals in the same subshell. If they're in the same subshell, that also means they have the same energy. So we can see here we have 3 2p orbitals all at the same energy. Similarly, we have 5 3d orbitals all at the same energy. So to illustrate what we mean by filling the degenerate orbitals one per orbital before pairing, let's take a look at an example. We can look at carbon, which if we're just following the periodic table to write out the electron configuration, you would have 1s2, 2s2, 2p2. If we were to draw this out with the orbitals, you would have 1s, 2s, then 2p. So we can label this as 1s, 2s, then 2p. So the s orbitals are pretty straightforward because we're going to put in 2 electrons in each. And we know that there's an upspin and then a downspin. So upspin, then downspin for our s orbitals. Within our p subshell, we're not filling the whole subshell. We only have 2 electrons. So you're going to put 1 electron in the first orbital and 1 electron in the second orbital. right? This is what we mean. You're not going to pair electrons in the orbital until each degenerate orbital has one electron. So you've got one per orbital here. All right. Let's take a look at a couple more examples of this. So let's say, for instance, we're looking at oxygen. Oxygen, if you look at the periodic table, is 1s2, 2s2, 2p4. So again, if we draw out the subshells, we're going to have the 1s, the 2s, and the 2p. 1s, 2s, 2p. The 1s is going to have one electron each, same with the 2s. For the 2p, we've got 4 electrons to fill the 2p subshell with. As we said with Hunds Rule, we're going to add 1 electron per orbital first. So that's used up 3. And now that we have 1 electron per orbital, we can pair that first orbital. So that is oxygen. We can take a look at another example. Neon. So neon's going to be 1s2, 2s2, 2p6. So when we look at this, 1s, 2s, 2p, we're going to fill the s, we're going to fill the p, or fill the 1s, we're going to fill the 2s, then we'll take a look at 2p, where we put in 1 electron per orbital, and since we have 6, we can pair, and we can actually fully pair all of the orbitals within that 2p subshell. Now, this is actually pretty notable because there is another concept that the MCAT likes to test students on when it comes to electron configuration, and that is these terms called paramagnetic species versus diamagnetic species. And we actually have an example of each over here. So, oxygen on the top, this is what we call a paramagnetic species. Paramagnetic essentially means that not all electrons are paired. So we can see here that within an orbital, we have 3 orbitals where the electrons are paired, but we have 2 that are unpaired. Another example of a paramagnetic species is carbon, where similarly we can see that we have some orbitals where electrons aren't paired. So over here, neon, everything is paired, so this is a diamagnetic species. And here, all electrons are paired. And this does have some significance between paramagnetic species and diamagnetic species. Paramagnetic species are attracted to magnetic fields. Okay. So that's how the Hunds Rule works for how we're pairing electrons within degenerate orbitals. Let's now take a look at some exceptions. These exceptions are looking at the concept at half or completely filled subshells. So this is the idea that half or completely filled subshells are unusually stable. And this affects the electron configuration, particularly when we're looking at the d block. And that's because when you have elements in the 4th and 9th columns of the d block, they're very close to having a half-filled d block with 5 electrons, and also very close to a filled d block with 10 electrons. So what these elements in the 4th and 9th columns of the d block will do is they'll actually move an electron from the s orbital to the d orbital to get that unusual stability of having a half or completely filled subshell. So we can take a look at a couple examples. So the first example we can look at is chromium. If you take a look at chromium on the periodic table, you can see it's in the 4th slot in the d block. And usually if you look at it, you would think, okay, if I'm following the periodic table, then this species should be argon 4s2 3d4. However, again, remember 3d4 is very close to half filled. So what chromium is actually going to do is it's going to move an electron from its 4s subshell into its 3d subshell to get that unusual stability. So that means this configuration you would get from the periodic table is incorrect, and the actual one is argon 4s1 3d5. Another example that we can take a look at is copper. Copper is very similar. Copper is the ninth element in that D block. So we can have copper, which just looking at the periodic table, you would think it should be argon 4s2 3d9. But again, since it's very close to that filled D block, it's not going to have this electron configuration. It's going to take one of the electrons from the 4s orbital and move it into the D block. So you end up with argon 4s1 3d10. Now, this is an exception that is tested on the MCAT. And one thing you might have been thinking about is, hey, if you take a look at iron over here, iron 2+, I also have 6 electrons after argon. Is this 3d6 going to shift an electron to the 4s subshell in order to also get this unusual stability? And the answer is no. So this anomalous electron configuration is not something that can be induced by removing electrons. It will only happen with atoms in their ground state, in their natural state. So that means for the MCAT, you really only have to worry about elements in the D4 and D9 columns. So that would be chromium, molybdenum, copper, silver, and gold. Those are the only elements where you have this anomalous electron configuration. Everything else is going to follow all the rules that we've just described.